Hey everybody, Mike here, and in today's video we are going to walk through a complete overview of all things minerals and rocks. Let's get started. So for this video we're going to be using this flowchart diagram that you can go ahead and download from the link in the description below. We're going to be filling it out as a way of organizing all of this information and making sense of things. And so without any further ado, let's jump right in by taking a look first at minerals. So if you will refer to the flowchart in this first box on the top left-hand corner, let's go ahead and title that minerals. And the first question we're going to try and answer is this: what exactly is a mineral? The way we're going to address this is by walking through the different criteria that must be met in order for a substance to be considered a mineral. And so let's jump right in and let's jot down these 5 criteria, and then we'll come back and look at them in some more detail. Here we go. So in this box here, we're going to say that minerals must be ... And here are the 5 main criteria that must be met for something to be classified as a mineral. First off, it must be a solid. It must exist in the solid state under normal conditions on Earth. To be a mineral, it must be inorganic. That means not living, never was living, wasn't made by living things, and essentially having nothing to do with life. To be a mineral, the object or the substance must be naturally occurring, and that is to say, it is not something that humans created in a laboratory setting or built or constructed any other way. It has to be something that exists naturally on Earth. Additionally, minerals must have a specific chemical composition as well as a unique crystalline structure. And if we could check all of these boxes, then it's likely that what you're thinking about is actually a mineral. But let's look at some examples. First off, here's an example of a shell. So let's just run through our criteria. Is it a solid? Yes, check. Is it inorganic? No. Shells are created by sea creatures. They're actually created as part of life, and therefore they are organic. So right off the bat, we know shells are not minerals. What about this plastic soda cap? Is it a solid? Yes. Is it inorganic? That's a little bit tricky to answer without more information. It's most likely made of some sort of petroleum product, and therefore indirectly it is organic. But more importantly, it is not a naturally occurring substance. This was clearly created within a factory of sorts. So not a mineral. What about this sample right here? This is a sample of something called pyrite. It's this interesting brassy yellow kind of crystal shape. It is definitely solid. It is inorganic. It exists naturally on Earth. It has a specific chemical composition. In this case, it's made of the elements lead and sulfur. And within this sample, there is a unique crystalline structure. And so, yes, this sample of pyrite is a mineral. What about this ice cube here? Well, this is a tricky one. It's definitely solid. It is inorganic. They exist naturally on Earth, right? There's a definite chemical composition, H2O, and there's a specific crystalline structure inside. So it technically checks all the boxes. However, if I were to push back, I would argue that under normal conditions on Earth, if you were to take the average temperature on the surface of the Earth, water would not exist as a solid. It would exist as a liquid. Certainly there are places on Earth where it's cold enough at our poles or at high elevations where water does exist naturally as a solid. But on average, that is one question mark. This is an interesting one to debate, so I leave that to you, and we'll move on to the next one. This interesting green crystal-y sample here. Yes, it's a solid, inorganic, naturally occurring, specific chemical composition and crystal structure. This is, in fact, the mineral olivine, very common on Earth, definitely classified as a mineral. Now let's look at one more. This is coal. So it's a specific type of coal called bituminous coal. It is clearly a solid under normal conditions on Earth. Let's skip the question of inorganic yet for the moment. It is naturally occurring. We see coal deposits all over Earth. It's made of carbon, so it's got a specific chemical composition and a crystal structure. Now back to the inorganic question. Most bituminous coal is formed from compacted plant remains. So think of a tropical rainforest and all the leaves and the foliage dropping to the forest floor, and then over millions of years getting compressed under its own weight. That's how coal typically forms. Therefore, it is not inorganic. It is organic, and it is not a mineral. So there's our quick look at what must be true for something to be considered a mineral. Now, on to the next big question around minerals. Well, how do I identify a mineral? Or in other words, what are some of the common physical characteristics of minerals that can help me to identify them? Keeping in mind there are in excess of 5,000 known minerals on Earth. So back to our flowchart, we're going to drop down to one section below, and we'll head it, minerals can be identified by ... So we're going to look at some of the commonly used physical characteristics, starting with color. Now I'm putting a note here that it's not reliable. So color is something you can use to identify minerals, but within certain constraints, and we'll talk more about that in a moment. We also look at hardness, which is typically measured using something called the Mohs scale, which is a scale of 1 to 10, with 1 being soft, minerals like talc, and 10 being hardest, with minerals like diamond. Next up is luster. Now, there are many types of luster. What luster is basically the way that light reflects off of the surface of a sample. There are lots of different types, but we're going to keep it simple and use the most basic examples of luster. Metallic. Does it look like a chunk of metal with a kind of glittery, reflective surface? Or is it non-metallic with kind of a flat or dull surface? Next up is streak. Interestingly, all this is what color does the mineral look like in its powdered form? Then we have cleavage and fracture, which in a very simple sense is how the mineral will break if you were to hit it with a hammer, for example. Minerals that display cleavage break in a predictable way. They might break into cubes or rhombi or thin sheets or something like that, as opposed to minerals that display fracture, which break randomly and unpredictably. Finally, I have kind of a catch-all, other. This includes things like taste and smell, which can be helpful in some cases, magnetism, fluorescence, refraction. There are a variety of these other characteristics that we can look at to identify minerals. But there's our basic list for now, and let's look at some samples and try and make sense of this, starting with color. Here are 3 minerals. Clearly very different colors. We have a clear, a kind of a smoky brown, and a bright purple here. Interestingly, these are all the same mineral. These are all samples of quartz. Quartz exists in just about every color in the rainbow, and therefore color, not super reliable. On the flip side of that, take a look at these 2 samples, both clearly blue minerals, but they're different. And so color is useful as a starting point, but definitely not your only identifiable characteristic. On to hardness. We mentioned this is how hard or soft a mineral is on that 1 to 10 scale. One of the ways we test this is with little pieces of glass, these glass plates, because we know that glass has about a 5.5 on that Mohs scale. And so if my mineral scratches glass, it's harder. If it doesn't scratch glass, it's not as hard. So that's just one of many tests. You can always use your fingernail. You can use a copper penny. There are a variety of ways that you can test hardness. Next up is luster. Here I see 2 samples. I have a sample of pyrite and I have a sample of potassium feldspar. The pyrite is clearly metallic. It essentially looks like a piece of gold, hence the nickname fool's gold. And this potassium feldspar has a much more dull, non-reflective pink finish or color, and so that would be non-metallic. Next up is streak. This, remember, is the color as a powder, and so the best way to test this is to rub your mineral on a rough plate, like a ceramic, the back of a ceramic tile, works well, and you'll get a little bit of the powdered version of the mineral and see what the color is. This sulfur gives you a nice yellow streak, and this graphite gives you kind of a grayish-black streak. Interestingly, some minerals look very different in their streak than they do in their actual solid form. Next up, cleavage and fracture. These are two examples of minerals that display cleavage. This is some halite on top and some galena on the bottom, and they both display cubic cleavage. So if you were to hit them with a hammer, the little pieces that would result would have this kind of cube shape to them. That's just one type of cleavage, though. Another example would be this muscovite mica, which peels into these thin, flexible sheets. So cleavage can come in many different forms. Fracture, on the other hand, is just simply random, unpredictable breakage, like this olivine and this sulfur here. And then finally, we get to the other category. So an example of a fluorescent mineral would be, appropriately, fluorite. If you were to shine a black light on this sample, it would kind of glow. Magnetite is a magnetic mineral. And then, of course, halite and sulfur have unique tastes and smells, and we could go on and on. But these are some of the key characteristics that we will use to identify minerals. Now, you might be wondering, well, why do the minerals have different characteristics? Why is it that fluorite glows under a black light? Why is it that galena cleaves into small cubes? Well, it turns out, and we're going to go down further on our flowchart here, that all of the characteristics of a mineral are the result of that mineral's internal arrangement of atoms. So we mentioned this before. It comes down to how the individual atoms are lined up and arranged within the crystal structure of the mineral. A great example of this is the mineral graphite and the mineral diamond, both of which are made of carbon. But those carbon atoms are arranged entirely differently in the two minerals, and so they have very different properties. Right? Graphite is soft, it's dark in color, whereas diamond is very, very hard. So that's just one example of how important the arrangement of atoms is. Now, that's all of our key information we need to know about minerals. What we're going to do next is we're going to transition into looking at rocks. And so I do want to point out in our last box here that all rocks actually are collections of minerals that are formed together. Think of it this way, minerals are the building blocks of rocks. So kind of file that way for a moment, and I just want to share a little bit more about minerals before we move on. So I'm just going to zoom out on my flowchart, and we're going to switch over to another graphic here. This is a table that was in the old version of the New York State Earth Science reference tables. This is a simple table that shows a handful of the most common minerals on Earth and their characteristics. So what I thought would be helpful would be to just kind of go down this list and quickly give you a little tour of some of the more common minerals on Earth so you can see what some of these look like and how their characteristics play out in reality. So we're going to start at the top here with our metallic minerals. We're going to look at 4 metallic minerals. And as we go through or go down the table, they are getting increasingly hard, and you can see that under the hardness column. So we'll start with number 1, which is graphite. This is a soft metallic mineral. It displays cleavage, though it's a little hard to tell. It gives you a black streak. It's used in pencils. This is what allows you to write with a pencil. You can see made entirely of the element carbon. Next up is galena. A little bit harder. It's got that interesting cubic cleavage. It's very dense and heavy for its size. So if you feel a sample of galena, it will feel heavy for how big it is. This is commonly used in batteries and as an ore of lead, and it's made up of lead and sulfur. Moving on, we have magnetite. This is our magnetic mineral that we talked about earlier. Contains iron and oxygen. It's a similar hardness to that of glass. Next up is pyrite, which we've talked about. Fool's gold has this brassy yellow appearance. Interestingly, though, it gives you kind of a greenish streak during the streak test. Contains iron and sulfur and will definitely scratch glass. Then we get to hematite, which is interesting because there are both metallic and non-metallic examples of hematite. It often has this kind of bold, earthy red, rusty appearance to it. It's used in jewelry, and it contains iron and oxygen. Then we jump down to the non-metallic minerals, starting with the softest one of all, which is talc. Yes, this is what's used for talcum powder, and if you feel a sample of it, it's smooth and soft. You could break it with your fingernails, and it's a really interesting mineral. Then you've got sulfur, yellow, smells kind of like rotten eggs, slightly harder, though still very soft. Selenite gypsum, very soft, used in drywall, so it's ground up and turned into drywall panels that are used in construction. Here we have muscovite mica, really interesting mineral. This is one of the ones that cleaves into these thin sheets. A little harder still is halite, which is salt, and if you taste it, it tastes like salt, often used to melt ice in the wintertime. Then we have biotite mica, kind of a sibling mineral to muscovite, and it cleaves the same way into these thin, flexible sheets, often used in construction materials, and a really interesting kind of unique structure with that interesting type of cleavage. Calcite. Calcite has an interesting characteristic. If you put acid on it, even a mild acid, it will fizz up, and that becomes a useful way of identifying it. Also with calcite, it's fairly transparent. If you look through it, it will double everything you see on the other side. It's called double refraction, and that's unique to this mineral. We have dolomite here, also will bubble with acid, but only when it's in a powdered form. We have fluorite, which we've already discussed. Interesting cleavage, though it's hard to see. We have pyroxene, used in jewelry. It's often black, but sometimes this kind of dark green color. And then harder still, amphibole and potassium feldspar. Potassium feldspar has this telltale pink color. Plagioclase feldspar, olivine, which is olive green, also used in jewelry, quite a hard mineral. And then we get to quartz, one of the most common minerals that exists on Earth. And then finally, garnet, which are these bold, dark red crystals, very common in New York State, and has a use for jewelry, used in abrasive because it's so hard. So that's a quick tour using our old version of the New York State Properties of Common Minerals chart, which again, you can download using the link below. I do want to also point out that New York State has updated its mineral flow chart. So instead of using that old one, now they use this interesting chart. It's kind of like a dichotomous key to help people identify minerals. It shows a lot of the same information, though it does have a few additional minerals on it. So let's flip back to our flowchart, and that brings us to the end of our minerals discussion, which means it's time to turn our attention to rocks. So on our flowchart, down beneath the minerals section, we're going to fill out our heading, and we're going to label that rocks. And so what I want to point out first and foremost is that rocks are classified based on how they form. We have three groups of rocks: igneous, metamorphic, and finally sedimentary rocks. These are our three large categories of rocks that exist on Earth. Now, I do want to point something out here, and you can watch some of my other videos for more details, but it's important to note that minerals make up rocks, and then rocks are in existence, but rocks change over time through a process that's known as the rock cycle. And this is just one way of visualizing this, but essentially any rock is constantly under attack from nature, whether it's being melted or pressurized or being weathered away by wind and rain. And so rocks change over time. Any rock could potentially turn into any other rock thanks to this process, the rock cycle. If you'd like to learn more about it, like I said, check out my other videos because we're not going to go into too much depth with that specifically in this conversation. So back to our flowchart here. And we're going to begin our conversation specifically looking at our igneous rocks. So down my flowchart, we're going to first head over to the middle and then up to the top, and we're going to label this box Igneous Rocks. And because this is the most important thing, we're going to fill this in by labeling how igneous rocks form. And what it amounts to is this. Igneous rocks form as the result of cooling and solidification of magma or lava. So they always involve melted rock in some capacity. In fact, the word igneous has the prefix igne, which refers to fire. These are rocks that are born of fire. Now, before we can really understand it, though, we need to know the difference between two of these words here, magma and lava. So let's take a quick look at this diagram of a volcano. At the end of the day, magma and lava are essentially the same thing. It's molten rock. It's melted rock material full of minerals, right? And the difference between these two terms is simply where it actually is. So magma is rock that is melted but is beneath the surface. It hasn't erupted and been exposed to the air yet. Whereas lava is molten rock that has been exposed to the air. So I want you to keep those differences in mind because they're very consequential when we look at the two main types of igneous rocks, which we're going to do right now. Starting with intrusive igneous rocks. So these are rocks that form when magma specifically cools and solidifies. Magma inside the earth cools and solidifies. And because it's so hot inside the earth, that process is very slow. It may take thousands or more years. The result is this. Rocks that form in this way have big mineral crystals because that slow cooling process allows crystals to grow and form. The most common, one of the most common rocks on Earth is granite. Granite is an intrusive igneous rock. And I can tell because I can actually see the mineral crystals. Those specks of black, that's biotite. The pink is potassium feldspar. The white is quartz. And I can see those crystals, which mean they're fairly large, and it must have formed inside the earth. Other igneous rocks have bigger crystals, like this pegmatite, which has very large crystals resulting from really slow cooling. And then kind of in the middle would be something like this gabbro that are medium-sized crystals. So those are intrusive rocks. Again, look for the mineral crystals. But then, as you might expect, we also have extrusive igneous rocks. And you might be able to guess, these are not slow cooling inside the earth. This is when lava on the surface cools and solidifies quickly. It may be a matter of seconds or minutes or a little bit longer, but this process happens very quickly when lava erupts from a volcano and cools off. Because it all happens quickly, the mineral crystals are either tiny or they don't form at all. And in fact, sometimes it happens so quickly that air bubbles may be trapped and you will end up with something called a vesicular texture. So again, let's take a look here. Here's an example. This is rhyolite. This is an extrusive igneous rock, and you can just barely see some of those black speckles, which are little biotite crystals, but they're tiny, almost not visible to the naked eye. Sometimes they'll cool so quickly we get no crystals, like this glassy obsidian. Cooled almost instantly, and there was no crystallization of minerals, so it's just one solid, shiny color. If we have air bubbles present, we will end up with a rough, bumpy, bubbly rock like this pumice, which has air bubbles in it. So we would call it a vesicular rock. All of those are examples of extrusive igneous rocks. Now, just like our minerals, we have a great table from the New York State Earth Science reference tables. This too is an older version, but I think it's really helpful for basic understanding of common igneous rocks and their characteristics. Grab your download with the link below. All right, back on our flowchart. So we've talked minerals, we've talked igneous rocks. We're moving on now to the second type of rock, which is our metamorphic rocks. So we're going to head over to the middle and then up to the middle of the page where we will title our second box Metamorphic Rocks. Now these have a different mode of formation. We're not solidifying lava or magma here. Rather, what we're doing is we're taking existing rocks and we're exposing them to intense heat and or pressure. Not so much heat that they actually melt, because then they would become igneous, but enough heat to actually alter the physical properties of the rock. Now, similar to igneous, we have two types of metamorphism that takes place. The first being contact metamorphism, and this one is more about heat. So imagine taking a rock, pouring some magma on it, and that magma burning the outside of the rock so that it changes its appearance. So that's contact metamorphism. Existing rocks are exposed directly to and physically changed as a result of contact with the intense heat of magma or lava. So this can happen inside the earth or on the surface. It's essentially taking an existing rock and burning it. We then have regional metamorphism, which is less about heat, though heat is still involved, and more about pressure. So here, existing rocks are exposed to prolonged periods of intense pressure and heat. Pressure that's often associated with the movement of tectonic plates. So we know the surface of the Earth is broken into large plates that move around, and that generates huge pressure, which creates these metamorphic rocks. Again, if you'd like to learn more about plate tectonics, definitely check out some of my other video content. Now, in terms of seeing these samples, one of the most telltale signs of a metamorphic rock is something called banding. And you can see that here in this sample of gneiss or this sample of gneiss. These are metamorphic rocks that have been squished by pressure so much that the minerals have actually aligned with one another to create these almost stripes within the rock. And usually those stripes are distorted. They're not perfectly flat. We may have lower grades of metamorphism, like this phyllite here, which has these kind of platy, foliated crystals on the surface that resulted from the pressure, or a very low-grade metamorphic rock like this slate, which is frankly kind of hard to identify because it doesn't have a lot of really distinctive characteristics to it. Just like with minerals and igneous, we have a great New York State reference table with common metamorphic rocks. You can grab that download below. Finally, our third type of rock would be our sedimentary rocks. So let's dig in here, head over to the middle of our table, and title our final box here Sedimentary Rocks. Now, there really are a few classes of sedimentary rocks to look at, but the main underlying idea behind them is that they form as a result of the compaction and cementation of sediments. Sediments are just bits of other rocks. And so if you imagine taking a bunch of pebbles and sand and things and squishing them together for a long time, not so much that you're changing the actual minerals, but enough that they kind of glue together into one new rock, that's what a typical sedimentary rock is. In fact, those are known as clastic sedimentary rocks, rocks that are compacted and cemented together sediments or fragments of other rocks. And these are classified based on how big those sediments are. So let's dig into that for a minute. Take a look at this photo of some different rocks on the ground somewhere. What you'll notice is that some of these rocks are big, like this boulder here. Some are smaller, like these cobbles and pebbles. And some are smaller still, like this sand, and I'm sure there's some silt and clay mixed in there as well. It doesn't matter what those chunks are made of. What matters is how big they are. We actually classify them into categories based on their size, starting with boulders, which are not on this graphic, all the way down, cobbles, pebbles, all the way down to clay. And that's important when you look at sedimentary samples, is to understand that they're going to look very different depending on how big the sediments are. So here are a few examples of clastic sedimentary rocks. On the left, I have a shale. And shale is made of clay particles compacted and cemented together, little tiny particles smaller than the naked eye can see. In the middle, I have more of a siltstone, similar idea, but made up of slightly larger sediments. And then larger still, I have my sandstone, made of sand grains compacted together. If you have bigger sediments, you might get something like this conglomerate with these rounded, smoothed out sediments on the left, or this breccia with these more angular sediments on the right-hand side. Those are very common sedimentary rocks on Earth. We do, however, also have some secondary types of sedimentary rocks that are considered either organic or crystalline. Starting with crystalline, these are going to be rocks that form when you have minerals dissolved in water. So think of like little sediments dissolved in water, and then they leave that water for some reason. They either fall out and settle to the bottom, or the water evaporates and leaves them behind. Either way, that will give you what's known as a crystalline sedimentary rock. We may also have an organic sedimentary rock, something like coal that forms from compacted plant remains, or coquina, which is shells compacted together. Let's actually take a look at some of these crystalline and organic samples here. On the left, I have some rock salt, which formed when salty seawater evaporated and left crystals behind. And beneath that, a dolostone, which forms when the mineral dolomite settles out of a dissolved solution. So those are crystalline sedimentary rocks. And on the right, I have some coal, which is compacted plant remains, and I have some coquina, which is a kind of limestone made from shells. Clearly, coquina and coal are considered rocks, but they're not made up of minerals because minerals must be inorganic. So they're kind of a unique class all to their own. As with our other types of rocks, we have a great chart from New York State with some common sedimentary rocks and their characteristics, and you can grab that download below. Now, to sum up our rocks, what it comes down to is how they form, whether it's igneous rocks from magma and lava, sedimentary rocks from weathered sediments, or metamorphic rocks from heat and pressure underground. Our igneous rocks are going to have things like crystals or glassy texture or vesicular air pockets. Our metamorphic rocks, we're looking for things like distorted banding. And our sedimentary rocks, we're looking for compacted sediments. And with that, we now have a beautifully completed flowchart covering all of our big ideas. I just want to point out, as I've mentioned already, you can download all sorts of resources using the link below, including different versions of the flowchart in color and black and white, filled in and blank, as well as all of these different tables and even some more that I didn't include in this presentation. And I will even upload this Keynote deck if you're interested in downloading it and taking a look or using it however you like. As always, check back regularly for new videos and be sure to go back and check out some of my old videos in which I explore in more detail some of the topics discussed here. As always, thank you very much, and I'll see you next time.